The paper discusses the issue of fairness in learning to rank models, particularly when demographic information is not available or is incomplete. It proposes a novel approach to ensure fairness by inferring missing demographic data using a probabilistic model. This method aims to mitigate bias and improve the overall performance of ranking models in various applications such as search engines, recommendation systems, and job candidate selection. The authors first provide an overview of existing fairness-aware ranking algorithms, highlighting their limitations, especially when demographic data is unavailable. They then introduce their proposed approach, which involves two main components: a demographic inference module and a fairness-aware ranking module. The demographic inference module uses a probabilistic model to estimate the likelihood of an individual belonging to different demographic groups based on available features. This inferred demographic information is then used by the fairness-aware ranking module to adjust the ranking scores and ensure fairness across different demographic groups. The authors also present an evaluation of their approach using several datasets, including a synthetic dataset and real-world datasets from various domains. The results show that their approach can significantly improve fairness metrics while maintaining or improving the overall ranking performance compared to baseline models. This paper delves into the integration of fairness in learning to rank algorithms, particularly in scenarios where demographic data is either unavailable or needs to be inferred. The authors explore how errors in demographic inference affect the fairness performance of different fair LTR strategies and their utility. They compare fair LTR and fair re-ranking type models, as well as the case where protected attributes remain hidden as a fairness strategy. The study reveals that re-ranking fair strategies are more robust to inaccurate inference of demographic attributes than fair LTR strategies. Fairness decreases as inference errors increase, suggesting that practitioners should proceed with caution and verify the quality of their inference tools beforehand. The paper also observes that fairness-unaware models show increased levels of fairness when working with incorrectly inferred demographic attributes, attributed to candidate items being wrongly classified as members of the alternate group. Fairness in machine learning is a critical concern, particularly in learning to rank models, which are often deployed in high-stakes applications. Despite its importance, fairness in LTR models has received limited attention, with most research focused on classification and regression tasks. This paper addresses this gap by exploring fairness in LTR models, especially when dealing with incomplete data. The authors propose a novel experimental methodology, which involves composing fair ranking algorithms into a spectrum of alternate strategies for integrating fairness into fair LTR pipelines. They introduce tools for inferring protected attributes and metrics for fairness and utility. The notation used in the paper includes the list of items to be ranked, attribute score vectors, and ground truth relevance scores. 3 models are introduced. ListNet, a fairness-unaware model that defines a loss function based on the top 1 probability. DELTR, a fairness-aware LTR model that aims to reduce disparate exposure while maintaining accurate score predictions. And DET-ConstSort, a fair re-ranking algorithm that enforces group representation within the top k positions of a ranking. The authors present a comprehensive analysis of the spectrum of alternate strategies for integrating fairness into popular LTR algorithms when the protected attribute is not known at test time. These strategies involve training models with or without protected attributes, and imputing or hiding the protected attribute during ranking and re-ranking. A detailed table summarizes the training, testing, and re-ranking aspects associated with each strategy. The paper's primary objective is to investigate the relative performance of alternate fair LTR strategies in the presence of unknown and inferred demographic groups, a critical open question in the field. By exploring this question, the authors aim to provide insights into the development of fair and effective LTR models that can mitigate biases and ensure equitable outcomes. Fairness strategies in ranking models are discussed, focusing on how they utilize protected attributes during training, testing, and re-ranking. 7 different strategies are presented, including oblivious, LTR, hidden, fair LTR, oblivious plus fair re-ranking, LTR plus fair re-ranking, and hidden plus fair re-ranking. Each strategy is detailed, highlighting the use of fairness-unaware models, fairness-aware models, and the role of inferred protected attributes. The importance of inference for missing protected attributes is also outlined, with 3 popular solutions for inferring sex based on available candidate attributes. The text discusses the use of first and last names to infer sex, leveraging supplementary parameters like email addresses or locations, and publicly accessible governmental data, and social media data. It also mentions the NAMSR service, which claims broad coverage across languages, alphabets, countries, and regions. The paper then shifts focus to fairness and utility metrics, including skew, NDKL, average exposure, and D-ADVA, ADVA exposure ratio, as well as NDCG for utility. These metrics are employed to assess rank fairness and utility in the context of ranking candidates. The experimental design section details the use of real-world datasets, including law, NBA, WNBA, Compass, and Boston Marathon, for training and testing models. The authors introduced 2 datasets, WNBA and Boston Marathon, comprising information on players and runners, respectively. Each dataset features attributes such as career points, seasons played, and average player efficiency ratio for WNBA players, and times at different stages for Boston Marathon runners. To identify disadvantaged groups within each dataset, the authors compute skews for each group at every position in the ranking. The experimental setup involves training 3 types of models: fairness-unaware models with protected attributes, and fairness-aware models requiring protected attributes. A controlled study is also conducted, where the level of errors in the protected attributes is varied, mimicking errors commonly encountered in demographic inference. Specifically, bidirectional and unidirectional errors are considered, where candidates are incorrectly inferred as belonging to a different group. To generate controlled test sets, the error level is varied from 0% to 100% in increments of 10%, and the process is repeated 5 times with different random seeds. Fairness metrics are computed using ground truth labels and averaged over all error levels. In a second study, real-world inference services are employed to obtain demographic attributes for 3 real-world datasets. The accuracy of each inference service is evaluated when provided with candidates' names from the datasets, with unrecognized names assigned to the disadvantaged group. The author's approach to measuring fairness and utility involves using the ground truth sex attribute to capture true fairness levels and the ground truth judgment scores for utility. The effect of wrong demographic inference on the fairness and utility measures of rankings generated by fairness-aware algorithms is analyzed. The authors of this research paper evaluate various inference services on real-world datasets, focusing on fairness and utility measures. They use Table 3 to provide an overview of the datasets, including the number of samples, disadvantaged group designation, and attribute used for inference. Table 4 displays the statistics of inferred protected attributes for each dataset and service, grouped by inference correctness and ground truth attribute values. The authors discuss the results of their controlled inference error evaluation, presented in Figure 1. They compare the fairness and utility measures of different models, including oblivious, LTR, and fairness interventions, under varying inference error rates. Oblivious, which does not explicitly optimize fairness, consistently shows a DADV, ADVA exposure ratio farther from 1.0 than fairness interventions for up to 1,520% error across all datasets. This suggests that fairness interventions are a sufficient and safe option for practitioners when the error is small enough. The authors also observe that opting for oblivious when subject to possible errors in protected attribute values is a better option than choosing LTR in terms of DADV, ADVA exposure ratio for up to 1,520% error rate. Additionally, OBLIVIOUS's value for NDKL is similar to those of re-ranking fairness interventions across different error rates, except for the WNBA dataset. For LTR, the DADV, ADVA exposure ratio rises with the inference error across all datasets until it eventually converges. Interestingly, group fairness emerges as a byproduct of erroneous inferences throughout the rankings, but for epsilon is greater than or equal to 30%. The initial disparity is reversed, and the advantaged group gets less exposure. The authors conclude that their results demonstrate the importance of considering inference errors when evaluating fairness and utility in ranking systems. This page presents the results of experiments evaluating the performance of various fairness strategies in the presence of inference noise. The strategies considered are oblivious, hidden, fair LTR, and oblivious plus fair RR. The experiments are conducted on 4 datasets: Law, W, NBA, Compass, and Boston Marathon. The results are presented in Figure 1, which shows the D-ADVA exposure ratio, NDKL, and graphs for the first simulation scenario. The ideal values are highlighted with red boxes on the y-axis. The results show that the hidden strategy is invariant to the inference error rate and outperforms the fairness strategies in terms of NDCG. However, the fairness strategies perform better in terms of D-ADVA exposure ratio and NDKL for inference error rates up to 1,520%. The fair LTR strategy shows a decrease in D-ADVA exposure ratio with increasing inference error rates, indicating decreased fairness. The NDKL tends to increase and then converge, while the NDCG tends to increase as advantaged or disadvantaged candidates receive a bonus or penalty and score due to incorrect inference. The oblivious plus fair RR strategy shows little variation in D-ADVA exposure ratio on the Law and Boston Marathon datasets, with the value initially reducing and then returning to its initial value. This is due to the fact that the group proportions between GDIS and GADV are swapped from the Detgestsort's perspective. Overall, the results suggest that the effectiveness of fairness strategies drops significantly with higher inference error rates, and that the hidden strategy is more robust to inference noise. The authors investigate the impact of inference errors on fairness and utility metrics in ranking systems that incorporate fairness interventions. They simulate inference errors by swapping the sex attribute values of candidates, ensuring the proportion of females is maintained at any top K positions in the ranking. The results show that Det-Constsort recovers the exact same ranking as when the inferred attributes are 100% accurate, and NDKL does not change much with error for oblivious plus phi RRR. For LTR plus FAIRRR, the DADV exposure ratio does not exhibit much variation with inference error in any dataset, due to the counteracting effects of providing the wrong protected attribute to ListNet and the perceived group proportions changing. The NDCG decreases and then converges across the increasing error level for the Law and Boston Marathon datasets. The authors also evaluate the performance of various fairness strategies on real-world datasets using state-of-the-art inference techniques. They observe similar behavior as in the error simulation studies, with oblivious yielding DADV exposure ratio values farther away from 1.0 than all the fair interventions. LTR exhibits a slight variation with smaller errors and a larger variation with larger errors. Hidden fairness strategies yield values close to 1.0 on Boston Marathon, whereas hidden overexposes the disadvantaged group. The authors conclude that in scenarios with high inference error rates, fairness models that require protected attributes may inadvertently lead to the advantaged group having lower exposure than the disadvantaged group. The authors evaluate fairness-aware learning to rank (LTR) strategies in the presence of inference errors. Results in Figure 2 show that the impact of inference errors on fairness varies by model. Fair LTR models, like DELTR, exhibit distinct behavior compared to fairness-unaware models such as ListNet followed by a fair re-ranker. The latter is more resilient to inference errors, maintaining fairness even with higher error levels. The study also examines the effect of hiding or inferring protected features when unavailable. It observes that wrong inference can improve fairness, as disadvantaged group candidates receive better ranks when misclassified. However, the authors caution that inference methods are unpredictable and should be heavily monitored or discouraged. FAIRLTR strategies, such as DELTR, maintain fairness with imperfect inference, achieving better fairness as inference accuracy increases. In contrast, strategies not relying on inferring protected attributes, like hidden, may provide lower fairness metrics overall. The authors acknowledge limitations, focusing on gender and binary demographic attributes, suggesting future work should explore other demographics and multi-valued attributes. The study concludes that the absence of demographic features affects fair ranking systems' effectiveness. Practitioners may attempt to overcome this by promoting fairness despite their absence or using demographic inference tools to infer them. The authors find that if inference is necessary, Fair re-ranking solutions serve as a more resilient alternative compared to fair LTR solutions. The authors of this research paper delve into ethical considerations in the context of demographic inference tools and their potential impact on fairness in machine learning models. They underscore that fairness is contextual, varying based on the problem, tools, and task at hand. The paper emphasizes the importance of understanding the potential drawbacks and benefits of using demographic inference tools, as well as the need for practitioners and policymakers to make informed decisions about their use. The authors also address their own researcher positionality as computer scientists and data scientists, noting that their perspectives may influence how they approach research problems and develop computational solutions to fairness issues related to digital tools. The research paper discusses the licenses and terms of use for various models and tools, including DELTR, Gender API, Behind the Name, and NAMSR. It also cites relevant papers on fairness in algorithmic decision-making, ranking, and name-to-gender inference services. The authors present additional results, such as NDCG results for the bidirectional scenario and case studies, which are displayed in figures 5 and 6. These results show consistent trends and a better interpretation of the fairness-utility trade-off. The results for the real inference service experiments are similar to the results for IN. The authors also present unidirectional results, including the DADV, ADVA exposure ratio, NDKL, and NDCG graphs for the second and third simulation scenarios, shown in figures 7 and 8. These results are discussed for each strategy, including oblivious, LTR, hidden, FAIR-LTR, oblivious plus FAIRRR, LTR plus FAIRRR, and hidden plus FAIRRR. Finally, the authors provide details on the model architecture, training, and parameter settings used in the research, including the training and testing stages, with an optional re-ranking stage, as shown in Table 2. The experimental setup involves training 3 learning-to-rank models for each dataset: a fairness-unaware model without protected attributes, a fairness-unaware model with protected attributes, and a fairness-aware model requiring protected attributes. The models are trained using the ListNet, DELTR, and det-const-sort algorithms. Figure 4 illustrates the training architecture, which includes input attributes, target scores, and protected attributes used in each model. The fairness-unaware models aim to reduce ranking errors, while the fairness-aware model aims to reduce both ranking errors and disparate exposure between 2 groups. Specific parameters are used for each algorithm, such as the gamma value for DELTR and the target distribution for det-const-sort. Trade-off graphs for the WNBA dataset show the relationship between NDKL as a measure of fairness and NDCG as a measure of utility. Figure 3 presents skew graphs for each dataset, with the disadvantaged group having skews below the green line. The authors discuss limitations and assumptions, including the need for careful tuning of the gamma value and potential inference errors. This section provides a detailed description of the experimental setup and results, emphasizing the importance of considering fairness in ranking models and the trade-offs between fairness and utility. Figures 5 and 6 present the results of experiments evaluating the performance of various ranking models in terms of NDCG at different cutoffs, specifically k equals 10 and k equals 50. The experiments are conducted on both simulated and real-world datasets. In Figure 5, the NDCG plots for the first simulation scenario, GDIS left-right arrow GADV, are shown. The plots compare the performance of oblivious LTR, hidden fair LTR, oblivious fair RR, LTR fair RR, and hidden fair RR models. The results indicate that the oblivious LTR model exhibits the highest wrong inference rates, ranging from 63.4% to 75.5% at k equals 10, and from 63% to 66.4% at k equals 50. In contrast, the hidden fair RR model demonstrates the lowest wrong inference rates, ranging from 35% to 45.5% at k equals 10, and from 35% to 40.6% at k equals 50. The NDCG plots for real-world use case experiments are presented in Figure 6. The plots compare the performance of GTR-UTH, GOPI, IBT, NNMS, and OR models. The results show that the GTRUTH model achieves the highest NDCG scores, ranging from 0.45 to 0.55 at k equals 10, and from 0.64 to 0.68 at k equals 50. In contrast, the OR model exhibits the lowest NDCG scores, ranging from 0.40 to 0.45 at k equals 10, and from 0.425 to 0.450 at k equals 50. These results suggest that the choice of ranking model and cutoff value significantly impact the performance of the system in terms of wrong inference rates and NDCG scores. The findings have important implications for the design and evaluation of fair ranking systems in real-world applications. Figure 7 presents the results of the second simulation scenario, evaluating the performance of various models in terms of fairness and ranking quality. The figure consists of multiple subplots, each displaying 4 key metrics: wrong inference percentage, d-adva, adva exposure ratio, NDKL, and NDCG. The wrong inference percentage, which measures the proportion of incorrect inferences made by the models, reveals that the oblivious LTR model consistently outperforms the other models, with the lowest wrong inference percentage across all datasets. Notably, the law and WNBA datasets exhibit similar trends, while the Compass and Boston Marathon datasets display distinct patterns. The d-adva exposure ratio, representing the ratio of the average exposure of the disadvantaged group to the average exposure of the advantaged group, indicates that the oblivious FairRR model achieves the highest exposure ratio, closely followed by the hidden FairRR model. Again, the law and WNBA datasets exhibit similar trends, while the Compass and Boston Marathon datasets display distinct patterns. The NDKL and NDCG metrics, which evaluate the ranking quality of the models, demonstrate that the oblivious LTR model achieves the highest NDCG scores, followed closely by the hidden LTR model. The NDKL metric measures the normalized discounted KL divergence between the predicted and true rankings, while the NDCG metric measures the normalized discounted cumulative gain. Overall, the results suggest that the oblivious LTR model outperforms the other models in terms of fairness and ranking quality, while the oblivious FairRR and hidden FairRR models achieve higher exposure ratios. These findings highlight the importance of considering fairness and ranking quality when developing models for real-world applications. This comparative analysis assesses the performance of various models, focusing on the d-adva, adva exposure ratio, NDKL, and metrics. The models under scrutiny are oblivious LTR, hidden fair LTR, oblivious FairRR, LTR FairRR, and hidden FairRR. The first set of graphs illustrates the d-adva, adva exposure ratio for each model across different scenarios, including law, WNBA, Compass, and Boston Marathon. This metric is crucial for assessing the fairness of the models in terms of exposure. The results show that the oblivious LTR model consistently has the highest d-adva, adva exposure ratio, indicating potential unfairness, while the hidden fair LTR model tends to have lower ratios, suggesting better fairness. The second set of graphs displays the NDKL values for each model, which is a measure of the difference in the number of documents that are incorrectly inferred as relevant. Again, the oblivious LTR model shows higher NDKL values, indicating more incorrect inferences, whereas the hidden fair LTR model has lower NDKL values, suggesting fewer incorrect inferences. The final set of graphs presents the IN metrics, which evaluate the ranking quality of the models. These metrics are essential for assessing how well the models are able to rank relevant documents at the top of the list. The results indicate that the hidden fair LTR model generally outperforms the other models in terms of NDCG, particularly at higher cutoffs such as overall. This analysis provides a comprehensive comparison of the performance of different models in terms of fairness and ranking quality. The hidden fair LTR model emerges as a strong performer, demonstrating both good fairness properties and high ranking quality. In a comparative analysis of various models, their performance is evaluated in terms of normalized discounted KL divergence, NDKL, and normalized discounted cumulative gain, NDCG, at 100, with varying error rates. The models under comparison are learning to rank, LTR, fair LTR, LTR fair RR, hidden fair RR, and oblivious fair RR. The trade-off between NDKL and NDCG is depicted for each model, showcasing their performance under different error rates ranging from 0% to 100%. This evaluation aims to assess the effectiveness of these models in maintaining fairness while optimizing for relevance in ranking tasks. The results indicate that the oblivious fair RR model consistently outperforms other models across all error rates, demonstrating its ability to balance fairness and relevance effectively. The hidden fair RR model also shows promising results, closely following the oblivious fair RR model in terms of performance. These findings suggest that incorporating fairness considerations into ranking models can lead to improved performance, particularly when using oblivious or hidden fairness mechanisms. This research contributes to the development of more equitable and effective ranking algorithms, crucial for applications where fairness is a critical concern. The results highlight the importance of considering fairness in ranking models, and the potential benefits of using oblivious or hidden fairness mechanisms to achieve improved performance. Ranking strategies in the study are categorized into four main groups: oblivious, hidden, fallible, and demographic attributes. The oblivious category includes strategies that disregard fairness and demographic attributes during ranking, comprising oblivious and oblivious plus phi RRR. Oblivious focuses solely on attribute relevance, while oblivious plus phi RRR incorporates fairness re-ranking to enhance diversity. The hidden category consists of strategies that hide certain attributes from the ranking model to assess their impact on fairness, including hidden and hidden plus phi RRR. Hidden removes specific attributes from consideration, whereas hidden plus phi RRR applies fairness re-ranking to promote fairness. The FAIR-LTR category optimizes for fairness directly within the learning-to-rank model, comprising FAIR-LTR and fallible plus phi RRR. FAIR-LTR aims to learn a fair ranking function, and fallible plus phi RRR combines this approach with fairness re-ranking for improved outcomes. Lastly, the demographic attributes category involves strategies that utilize demographic information to enhance fairness, including demographic adder and demographic adder plus phi RRR. Demographic adder considers demographic information in the ranking process, and demographic adder plus phi RRR adds fairness re-ranking to this approach. Figure 10 provides a visual representation of these ranking strategies, illustrating their interconnections and how each strategy builds upon or modifies previous ones. This figure serves as a valuable reference for researchers seeking to understand the complex relationships between these approaches and their implications for fairness in ranking systems.